Hi everyone, I am Madan Thapa Chetri. I am your TA of CE122 Fluid Mechanics. So today we will be going through some of the homework problems that are assigned for this week 2. So I will go through the some fundamental basics first questions, and then there is some question related to viscosity, and then there is also question related to manometer problem solving. So let's begin with first question, which is pretty easy as well. And let me write the question first, so I can explain you in more detail while I write and when I solve as well. So let us begin. So first question asks. So first question asks about like if the density of the air increases by a factor of 1.4 times due to the uh, temperature change. So what will happen? The question asks about what will happen to specific gravity, specific weight, this in whether it increases by same like with the density 1.4 times, or same increases by 13.7x, remains the same. So here what we need to understand is let us know about this specific weight, what it means. So basically specific weight, this specific weight gamma is equal to density times acceleration due to gravity. So here our main focus is on density, since it increases by 1.4 times, and acceleration due to gravity is constant, which is 9.81, so it remains constant throughout any process. So this specific weight gamma will increase by 1.4 times as well. So our answer for the first question, our answer is option A. So let us begin question number 2, which is related to finding the dynamic and kinematic viscosity of kerosene, SAE 1020 meter. So I'll write the first question and then talk. So let us begin. I will be using the figure A2 and A3 from the book. So let us begin with first kinematic viscosity, because it lies in kinematic viscosity. So kinematic viscosity, we will write that as nu. Yeah, we will write that as for kinematic viscosity. For oil, kerosene, and water. So what will be the value for this? So by using the figure A3, so we get for oil we get 4.5 into 10 to the power minus 5, and for kerosene we get 1.5 times 10 to the power minus 6, and for water we get 5.5 into 10 to the power minus 7. So all these are from figure A2 and A3. It's on book. So let us go with another one, dynamic viscosity. Dynamic viscosity mu. So for oil, we will our value is 4 into 10 to the power minus 2, and for kerosene our value is 1 into 10 to the power minus 3, and for water our value is 5.5 into 10 to the power minus 4. So these are the directly from the figure. So when we line our when we go vertical from the 50 degrees Celsius, and when it intersect the uh, specific these properties like kerosene, motor oil and water, and we will just get the value of these kinematic and dynamic viscosity. So this was for question number 2.12. So let's begin another question which is also fundamental questions related to bulk modulus. So I will go through that. So let's begin question number 2.2. So it's the conceptual question. So for question number 2, so it asks about dimension of bulk modulus of elasticity, or whether it is the same. It has the same dimension of pressure by density, or for option B, it asks it says that the same as the dimension of whether the bulk modulus has the same dimension as of pressure by volume, or it has the same dimension as of pressure. So what we need to understand is, first we need to understand what is bulk modulus. So bulk modulus of elasticity is the change in pressure, the ratio of change in pressure by fractional change in volume, which is equal to minus del P divided by change in volume divided by volume. So from this equation, also I want to emphasize one thing. So bulk modulus is used to quantify the degree to which a liquid is compressible. So this all help us to find the compressibility. And here from this equation, and our question asks whether the dimension of bulk modulus is same as pressure, or same as pressure divided by volume, or pressure divided by density. So here we can clearly see that since this is fractional change, so it will be dimensionless, and so our only remaining parameter or unit is change in pressure. So so for our 2.2, our answer will be option C. So that is the dimension of bulk modulus of elasticity are the same as the dimension of pressure. So next, for the next question, I will be dealing with capillary rise water column problem. So let's start question number 2.47. It is, I already draw the figure, so it can be easy to explain. So I will not write the question here because it is long. So for 2.47, the question asks a water column in a glass tube is used to measure the pressure. So this glass tube is used to measure the pressure of in a pipe, and this pipe, this tube is 1 by 2 inch of in diameter, and so the question asks us to find how much of water column is due to surface tension effect. So how much is this uh, height is due to the effect of surface tension. So question clearly mentioned we need like there is connection between surface tension and pressure as well. And so also for question further asks us to find the depth, find the height of that water column if the diameter is changed to 1 by 8 or 1 by 16. So let's assume, so let us directly go through the formula for capillary rise of water in a glass like this. So our formula is del H is equal to 4 times surface tension divided by specific weight times diameter. So here we already have diameter, which is 1 by 2 inch in first case, and in second case our is 1 by 8, and in third case 1 by 16 inch. So before we use this value in this equation, first we need to find this surface tension and this specific weight. So let us assume a standard fluid properties, as you can see in this slide 23 of the class materials as well. So at 20 degrees Celsius, specific weight of water, gamma will be 62.4 lb per feet cube, and surface tension of water will be equal to tentatively equal to 0.0050 lb per feet. So since we already have value for specific weight, density, what we need? We need just this diameter, and we have already diameter for this tube as in the form of 1 by 2, 1 by 8, 1 by 8 inch. So here one of the trickier part is you need to take care about the unit conversion. Since here I have already written in the form of feet, so our diameter is in inch, so we need to convert that into feet. So for let us do for 1 by 2 inch. So for 1 by 2 inch will be equal to 1 by 2 into 12 feet. So when we put this value in this equation 1, then our del H will be 4 times surface tension of water 0.005 divided by specific weight 62.4 into this diameter is 1 by 24, which will be equal to 0.00769 feet, and when we convert that into inch, then it will be equal to 0.0923 inch. So similarly, what we can do is we can do same thing for 1 by 8. So I will do here. One by 8. So we have already the 4 times this surface tension 0.005 and 62.4 into 1 by 8 into 12. So that give me 0.031 feet, and when we convert that into inch, our value will be equal to 0.372 inch. So same thing for 1 by 16 inch as well. For 1 by 16 inch, our del H will be equal to 0.0615 feet is equal to 0.738 inch. So one thing you may notice as well, 0.738 inch. So one thing you may notice here is when we decrease our diameter of this tube, then surface this capillary rise is increasing. So that's the one of the thing you need to take care about why it might increase. So let's go to question number another one. It's 3.16. It is interesting. It is related to computing the specific gravity and pressure at gauge C. So now let us begin question number 3.16, 3.16. So it asks us about the finding the specific gravity of oil and pressure reading at gauge C. So first let me draw the figure. So this is our figure, and question asks about finding the specific gravity of oil and pressure at sea. So what we can do is we can use the hydrostatic pressure variation with depth, that is del P is equal to rho g h. So basically this is specific specific weight. So what we can do is, since we are coming from air to we are coming down from air to oil. So here the question asks us to find the specific weight of oil and pressure at sea. So we can use the principle of hydrostatic pressure variation with the depth, that is del P rho g h, and this will give us specific weight. And at the temperature at this temperature T is equal to 10 degrees Celsius, specific weight of water at temperature is equal to 10 degrees Celsius, density of water will be equal to 1000 kg per meter cube. Thousand per meter cube. Similarly, our acceleration due to gravity will be equal to 9.81 meter per second square. So we know density of water at 10 degrees Celsius of water is equal to 1000, and acceleration due to gravity is 9.81, and for finding the specific gravity of oil we can see here one of the interesting thing, something like when we go down, when we come down from upper, like you can see here PA is equal to 50 and PB is equal to 58.5. What we can notice is when we go down, then pressure is increasing. And let us compare between this A and B and use this formula so we can compute the ratio of specific weight. We can compute the specific weight. So between this point B and point A, so our PB, so we will use this formula. PB is equal to PA, so it's the difference between PB and PA plus rho G as rho density of water, rho no density. So for finding the specific weight of water, oil, we will be compare the gauge A and gauge B because we are in the air and oil interface, and air pressure is also uniform. So let me write this equation into this point A and point B, or air and water, air and oil interface. So for which will give us PB is equal to PA plus this rho GH. So we will be computing rho of this oil, rho oil times G is constant, G is G into H what we don't know is, we don't know just this. We know this, we know H is equal to this 1 meter. So we will put that in equation. So our PB is equal to 58.5. So let us convert that into Pascal. And 50,000. We don't know this rho. And we know 9.81 G, and our H is 1 meter. So we, based on this, we just need to compute this density of oil. So density of oil will be, when we take out this, it will be 8,500 divided by, so this will give us rho oil is equal to 8,500 divided by 9.81. So that means just 866.46 kilogram per meter cube. So this is the density for oil. And what we know? We know, so we computed density of oil as 866.46 kilogram per meter cube, and we know this, I have already mentioned this rho specific weight is equal to rho g, but we will be not using that here, since we know specific gravity of is the ratio of oil density to the so specific gravity of oil is equal to rho oil by rho water, density of water. Since g they will cancel out, and our specific density of oil is 866.46, and our density of water is equal to this 1000. So this will give us 0.866, that is equal to 0.87. So here what we did, we simply applied this change in pressure hydrostatic formula using this formula, this density times acceleration due to gravity times height. So based on that we computed density of oil, and from that density of oil we used the this is specific for finding the specific gravity of oil. We just use density times g divided by density of water times g, and we got 0.87. So it may be confusing as well, but once you know this just this formula, then it will be pretty clear. So we also need to find pressure at this point C, and we will use here like this oil and water surface, because we already know pressure at PV, and we will use the same formula here as well. So to find the pressure at gauge C, we move down from gauge B to gauge C, crossing this remaining oil surface, and entering into water layer. So our PC will be equal to PV. Same thing, we will be doing same thing. Rho of oil, we will need to consider this small gap as well. Rho oil into, we already know this, and G times H plus we will be entering into this water surface. So we know density of water as well, density of water times G times H water. This is H oil. So we don't know this PC, we know PV. So let us convert that 58.5 kilopascal into pascal. So it will be 58,500 plus density of oil, we know already, it's 866.46 kilogram per meter cube, times we know acceleration due to gravity is 9.81 meter per second square. H of oil is in 0.5, plus density of water we know it's 1000 kg per meter cube times 9.81 into H of water is 1 meter. So when we compute all these together, we get 72,560 pascal, so which will be equal to 72.56 kilopascal. So as you see, so this will be equal to now 72.56 kilopascal. Here you see, when we are in the top air surface, the pressure was 50, and when we are in pressure at the surface of wheel, pressure was 58.56, and when we come down again to pressure, so it's 72.56 kilopascal. So it shows that pressure increases linearly when we go down. So now let's go to question number 3.37, which is a problem related to manometer. So I will first draw the figure, and then I will try to explain the figure and what we need to find. I will explain that in next. So let us start question number this 3.37. 3.37. So the question asks us to find the pressure at center of pipe B. So here question asks PB is what? So to find the pressure, to find the gauge pressure at the center of pipe B, we can use the manometer equation starting from this open end. So we can call that as A for now, and up to here. So let me write the hydrostatic pressure equation. So it is given as del P is equal to rho G H. We know what is this? It's specific weight times H. So here we are given a specific weight for two different column. Like for this column it is 20, and for this second pipe B it is 10. So we will be using this. So let us begin from pressure point A to point B using same approach that we did in last question. So let me begin. So our PB we don't know. We need to compute that, and we let us assume this as pressure A for now. Pressure A, and when we go when we come down from pressure A to this point, then it will increase. So we will add that pressure term. So that is equal to specific weight. Let us consider that this as rho 1. No. This gamma 1, and we only need this H, and we need to climb this as well with the same gamma specific weight. So we will consider that as well, but we need to subtract that here. So that will be rho. Let us consider this as H1, and rho 1 times H2. So this is for this part, this pipe, and again we need to climb up to this center of the B. So that will give us again minus, and let us consider this as rho 2 and this as rho 1. So rho 2 times S3. Let us consider this as S3, this one as S2, and we need to compute here this H1 is unknown. So here it's tricky. As you already see here, it's 3 by 4 and it's rectangular. So for a 3, 4, 5 triangle, this if we have 3, 4, then obviously this hypotenuse will be 5. So based on that formula, we need to compute this as one. What will be this as one? So we know this length is 50 centimeter, and when we consider this 3, 4, 5 triangle, then height of inclination will be equal to 0.5 times 3 by 5. That will be equal to 3 0.3 meter. So our major problem is solved. what we need next is we just need to plug those value into this equation. We don't, so pressure A, since it is exposed to air, we can consider that as pressure as 0, and we know specific gravity of this column, it's 20 kilonewton. 20 kilonewton into, we know H, we just computed 0.3, and for same like 20, and for this small part it's 0.1, and when we go up, then this specific weight is 10 into S3 is 0.5. so since it's 0, so what we do is 20 into 0.2 minus this will be 10 into 0.5, it will be 5. So when we compute this overall, we got negative pressure at this point. So this sums of our first week recitation class. What we have covered in this recitation class is some fundamental questions related to fluid properties, and we also learned about using the chart to find the dynamic and kinematic viscosity as well. We learned how to find the depth of, find the height of capillary rise as well, and we also see or understand the concept of tank pressure and some manometer rules as well. So thank you for this week. So I will come next week with another video for week 3 recitation class. Thank you everyone. Thank you for your time.